Start with the important distinction. eBPF is not malware. It is a Linux kernel mechanism for safely extending networking, tracing, observability, and security behavior without loading a traditional kernel module. A user space loader asks the kernel to load a program. The verifier analyzes control flow, register state, memory access, and helper usage. If accepted, the program can be interpreted or just-in-time compiled, then attached to an approved hook. That safety boundary is powerful, but it answers a narrow question. Can this program execute without violating the kernel's rules? It does not prove the operator is authorized or the program's purpose is benign. An eBPF rootkit is therefore best understood as abuse of legitimate programmable kernel infrastructure after an attacker gains the required capability or exploits a vulnerability. The defensive challenge is not to fear eBPF. Draw the normal telemetry path. A process opens a file, starts another process, creates a network connection, or crosses a security decision point. The kernel exposes attach points such as trace points, probes, group and networking hooks, or Linux security module hooks. An approved eBPF program runs at that attach point. It can read permitted context, apply a small policy, update a map, or send an event through a ring buffer. A user space agent consumes those events and forwards them to an endpoint platform or security information and event management system. Notice the trust chain. The security console does not see the original kernel event directly. It sees an event selected and shaped by kernel code, the attached program, shared maps, the collector, and the transport. That architecture gives defenders efficient, high-volume visibility. It also creates a decision point. If an attacker can influence one layer in the same observation path, what independent evidence remains to validate what the sensor reports? Now place the attacker on the diagram, but keep the sequence honest. Modern Linux kernels gate BPF operations through privileges and capabilities whose exact requirements depend on kernel version, program type, attach point, and distribution configuration. Older systems often rely broadly on administrative capability. Newer systems separate responsibilities with capabilities such as BPF, performance monitoring, or network administration. So ordinary unprivileged malware cannot simply declare itself a kernel rootkit. The attacker typically needs elevated access, a dangerously overprivileged container or service, a compromised approved loader, or a vulnerability that crosses the boundary. Once that boundary is crossed, an unauthorized program may attach where it can observe, filter, redirect, or influence a security-relevant path. A companion user space process may reload programs at boot or orchestrator startup and coordinate state through maps. The practical detection question is not only, is BPF running? It is, who loaded this specific object, from which artifact, under which change record, with which attach point and capability set. Rootkit does not mean magic invisibility. An abusive program may suppress selected events before a particular collector receives them, modify a policy outcome, redirect network traffic, or create a clean-looking view for tooling that trusts the same compromised path. But every attach point has scope. A program that blinds one endpoint stream may not erase a switch flow record, a cloud load balancer log, an identity event, immutable audit storage, or a second sensor anchored in a different mechanism. This is why the strongest visual is two parallel arrows. The host reports no unusual connection, while an external network control reports traffic leaving the machine. Or the runtime inventory shows a program and link that the deployment system cannot explain. Treat disagreement as a high-value signal. Do not claim that any eBPF technique bypasses every kernel or security product. The engineering principle is narrower and more useful. A sensor cannot be the only authority for its own integrity. Put a decision diamond around every loaded program. Is the program expected on this host role? Does its identifier, tag, build digest, map set, and attach point match the approved deployment? Which process loaded it? Which package, container image, service unit, or orchestration change explains that process? Was the capability granted deliberately? Build a baseline that records programs, maps, links, attached targets, owners, pinned objects, and expected lifetimes. Ephemeral does not mean unimportant. A short-lived program can still be suspicious if no authorized workload explains it. Monitor the loader as carefully as the loaded object. Audit creation and attachment where supported. Alert on new privileged processes, capability changes, unexpected pinned objects, anomalous program churn, and VPF activity outside the maintenance pipeline. The verifier's acceptance is not your allow list. Operational provenance is the control that turns a technically valid program into an authorized one. Build the defense in layers. First, reduce authority. Disable unprivileged BPF where workloads do not require it, and verify the actual behavior of your distribution and kernel. Remove broad administrative capabilities from containers and services. Grant only the capabilities and attach rights an approved loader needs. Second, constrain loaders with mandatory access control, SecOmp, service sandboxing, immutable images, and tightly governed deployment identities. Keep kernels and eBPF tooling patched. Use secure boot, kernel lockdown, measured integrity, and signed or verified software supply chains where supported. Third, create runtime visibility. Continuously inventory programs, maps, and links from trusted tooling. Correlate the objects with process, package, container, and change management provenance. Finally, add independent vantage points, network infrastructure, cloud control plane logs, identity telemetry, hypervisor, or hardware-rooted measurements, and append only remote logs. No single control carries the whole design. Prevention narrows who can load. Inventory exposes what exists. Provenance explains why. Independent signals reveal contradictions. When you suspect kernel-level tampering, speed matters, but so does evidence. Isolate the host through controls the potentially compromised machine cannot override. Preserve volatile state before blindly detaching programs or rebooting. Capture the current program, map, link, attach point, and pinned object inventory using trusted response tooling. Record loader processes, parent chains, capabilities, service units, containers, kernel and audit logs, package history, and external network evidence. Then revoke credentials and tokens the host could access. Examine peer systems for the same artifact, loader identity, image digest, or deployment path. Determine whether the compromise came through excessive privileges, stolen orchestration credentials, a vulnerable kernel, or a tampered software supply chain. If kernel trust cannot be reestablished, rebuild from trusted media or a known good immutable image. Do not treat removal of one visible program as proof of recovery. The common pitfall is destroying the best evidence first. A clean response separates immediate containment from later eradication and preserves enough context to close the original access path. Finish with the checklist. Patch the kernel and supported eBPF toolchain. Disable unprivileged BPF where it is unnecessary and verify the setting across your fleet. Remove broad capabilities from containers and long-running services. Restrict approved loaders with mandatory access control and service sandboxing. Maintain an inventory of programs, maps, links, attach points, pinned objects, loader identities, and expected lifetimes. Tie every object to an approved artifact and change record. Alert on deviations, capability changes, unusual churn, and loaders outside the deployment pipeline. Protect boot and kernel integrity. Use verified images, secure boot, or measured integrity where appropriate, and remote append-only logging. Compare endpoint telemetry with network, identity, cloud, and platform signals that do not share the same trust path. For response, isolate through external controls, preserve volatile BPF state, revoke credentials, hunt the fleet, and rebuild when kernel trust is uncertain. Avoid three traps: treating eBPF itself as malicious, believing the verifier proves intent, and asking one sensor to certify its own integrity. Copyright 2026 CipherVibe. All rights reserved.